All right, hi everyone. We're going to talk about transformations today. And if you think about what that word means, to transform something means to change it. So what we're really talking about today is if you take an equation and you graph it, and then you make some sort of change to the equation, how does that change the graph? All right, we're going to start off by going over some common functions you guys have seen before. The reason we're doing this is if you're going to transform something, you have to have something to transform. So this is going to be like our starting point for these problems. We're going to start with these equations and start with these graphs, and then we're going to change the equations and see how it changes the graphs. So we're going to call this our library of functions. It's a collection of functions. Everything we talk about right now should be something that you have seen before, nothing new yet. But we will add to our library throughout the year. We will start seeing more new functions. So here's the first one, a nice simple one that you saw way back in probably freshman year or even junior high. It's a parabola. And the equation for a parabola is f of x equals x squared. Now that's the most simple parabola you can do. It's just x squared. But again, we're going to change that equation and then see how it changes the graph. Okay, here's another pretty common one, not quite as common as the parabola, but this is the graph of the square root of x. This is the one we did in our activity yesterday. Basically what it is it's a x squared graph tipped over on its side and the bottom is chopped off. So it's kind of like half of a parabola going sideways. This one is the absolute value of x. If there's one in here that you might not have seen before, this would probably be it. Absolute value is the function that just turns every number positive. So basically all of our answers are positive. That's why it's all on the top of the graph. And it's that perfect V shape. It's those two perfectly diagonal lines that cut the first and second quadrants in half. This one's x cubed. This one you guys probably saw last year. And if you look at the right half of it, it looks kind of like a parabola. But instead of coming down and twisting back, or instead of coming down and turning back up, it comes down and twists, and on the left-hand side you have kind of what looks like an upside-down parabola. And then our last one, this is the cube root of x, and this one looks kind of like that one tipped over on its side. Or another good way to think about it, if you block off the left side of this, it looks a lot like the square root of x. But where the square root of x just stops at 0 because you can't take the square root of a negative, you can take the cube root of a negative, and that's why you get that tail part on the left-hand side. All right, that's our library of functions. We're going to start with those graphs, and then we're going to transform or change them. So here are some general rules for transformations. Basically, break it down into x and y. X is always a horizontal component. When you're plotting just a single point, x tells you how far to go left or right. If it's positive, you go to the right. If it's negative, you go to the left. But it's always a horizontal component. So any change to x is going to be a horizontal transformation. You might shift your graph to the right or the left. You might reflect it to the right or to the left, or you might stretch it to the right or to the left. Now, f of x or y, which are for this problem essentially the same thing, that's your vertical component, which means it's a vertical change. So if I make a change to y, or f of x, that transformation is always going to be vertical too. Another thing that's interesting that you'll see as we move through these, any change to x, I said in here it's backwards. When I put a word in quotes, it means it's not a real math term, it's more of my description. But what you'll see is, like, when you make a positive change to x, you would think to yourself, oh, positive to the right, that's great. That actually goes to the left. Or when you make a negative change to x, that would go to the right. So those end up being kind of the opposite of what you think. And then one last little hint for this. When you're doing your transformation, a lot of times it's easier to focus on one point at a time. It's easier to do a shift or a stretch or a reflection to a single point than it is to this twisty, turny shape. So if you're stuck trying to do these transformations, choose a point or two, focus on those, it'll really help you out. All right, the first transformation I want to talk to you guys is about shifting, which is when you just move the graph. You can move it up, you can move it down, you can move it left, you can move it right. We'll do the vertical shifts first, either up or down. And that's when you take your function, f of x, whatever it is. Remember, we can do these transformations to any function. That's what's good about the transformations. It's not just our library of functions, it's absolutely any function. So if I take my equation for f of x, and I either add or subtract some number to it. So I have f of x either plus or minus c, we'll call it. If you add that number, if you add or subtract, if you add a number, it's just going to take the graph and move it up that many spots. If you subtract a number, or another way to think of it is adding a negative, you move down that many spots. So it's a very simple transformation. This, I think, is the easiest one of all. Here's one example of that. For each one of these, I picked one example from our library, and I showed you an example of that transformation. So in red, what you see is the absolute value of x. That's copied straight from our library of functions. And in blue is the absolute value of x minus 3. So because I stuck that minus 3 on the end, I subtracted 3 from the function. All it does is it takes the absolute value graph, slides it down 3 spots, and it's there instead. Okay, here's the horizontal shift. Now remember, on the first slide, or one of the earlier slides today, I told you guys, when you make a change to f of x, that's always a vertical change. But when you make a change to x, that's a horizontal change. So if I go back a slide here, which it's not letting me do, that's okay. If you jump back a few seconds on the video, the last one we did f of x and we put the plus or minus c on the end. So we were adding it to f of x. That makes the change vertical. Now this one, if you look at the slide, we're adding to x, not to f of x. And if I make a change to x, that does a horizontal transformation. So basically, by adding a constant to x, it shifts the graph horizontally. And remember what I mentioned earlier about how it's backwards. It's the opposite of what you'd expect. You'd think if I take x and I add 3, it moves 3 to the right because that's positive. It's actually the exact opposite. So if you add a number to x, it moves to the left. And if you subtract a number from x, it moves to the right. And here's an example of that. So in red is our ordinary parabola, x squared. Again, copied straight from our library of functions. And in blue is x plus 2 in parentheses squared. So I added 2 to the x. See, I didn't take the x squared and put a plus 2 after it. That would have shifted it up 2. I put the plus 2 in the parentheses with the x, and that makes it a horizontal shift. All you have to do is remember it's backwards. So when you see the x plus 2, probably your initial reaction is, okay, it's plus 2, I'm going to go 2 to the right. Just remember it's actually 2 to the left, and that's where the blue one came from. Okay, reflections. A reflection happens when you make something negative, or a good way to think of it, probably a better way to think of it, if you multiply by -1. If you multiply anything by -1, it will end up being a reflection. So if I take my whole function, f of x, and I multiply it by -1, I get negative f of x. That's a vertical reflection. Remember, anytime I do something to f of x, it's vertical, and anytime I do it to x, it's horizontal. So multiplying your function f of x by a negative number reflects the graph vertically or across the x-axis. Anything from the top flips to the bottom, anything from the bottom flips to the top. And remember, when I say the word reflection, it's like a mirror image. So here's an example using square root of x. In red is regular square root of x, straight from our library. And in blue is negative square root of x. So because I took that function and multiplied it by -1, essentially, I put a negative sign in front of it, it took it and it flipped it from the top to the bottom. Now, if you follow the patterns that we've been talking about, The next one would be f of negative x. So remember we said if I multiply f of x by a negative, that's a vertical reflection. If I multiply x by a negative, it's going to be the horizontal reflection. So multiplying x itself, not the f of x, but the x, by a negative number is going to reflect it left and right, horizontal, or it's going to reflect it over the y-axis this time. And for my example, I did square root of x again. We'll look at the exact same function. So in red, same as before, square root of x. Now in blue, this time on the last slide, I had the negative in front of the square root sign, and that reflected it up and down. This time the negative is inside on the x, and that flips it left and right instead. Okay, the last transformation I'm going to do is the stretch. And I put it in quotes again. That's my word. The actual mathematical word for it is it's called a dilation, but I like to call it a stretch instead. I think that's a much better description of what it is. So this is when you take your function f of x and you multiply it times any number. We'll call it a c for a constant. So you have c times f of x. That takes it and it actually stretches out your graph. Now this is what's called a non-rigid transformation. It's the only one that we've learned so far that is a non-rigid. Now rigid means like concrete or stone. It is what it is and it doesn't change. Non-rigid means soft, stretchy. It does change. And that makes this the hardest transformation. If you're just doing a shift, that's easy to visualize because it's just moving. Even a reflection, yeah, it's a mirror image, but it's still the same shape and size. It's just pointing a different direction. This one looks different. You know, you're going to warp it, you're going to change it, it's non-rigid. It'll change shape and it'll change size when you do this one. So basically, what you're doing is you're changing the height of the function. If I have f of x and it's here, and I multiply it by 5, it makes it 5 times as tall. Or if I have f of x is here, and I multiply it by 3, it's 3 times as tall. If I have f of x is here, and I multiply it by 1/2, it's 1/2 as tall. It's actually not a stretch, it's more of squishing it or compressing it. But that's what you do, you're changing the height, and it is non-rigid. So here's an example right here. So I use square root of x again for the 3rd time in a row in red, and in blue I multiplied it by 3. And you can see it's not the same shape or size. It looks like a different graph. It's been stretched out. So a good way to think of this one, when you're doing this transformation, imagine this point right here on the axis, you're pinning that one down. You're nailing that one down. That one's not going to move. When you do a stretch, anything that's on the axis stays right where it is. And then imagine the red arrow, I pinched it and I pulled it up and that thing stretched like a rubber band. You know, it actually stretches, it moves, it changes. But that purple point I marked, that stays where it is. Now, a good way to get the stretch down is to focus on one random point. So let's say I choose this point right here. However tall or however high that point is, this point here should be 3 times as high. So there should be another one of those here and another one of those here. 1, 2, 3 equal pieces. If you stretch it out, that should work for every single point on there. Every single point should be whatever this number is here, because I was multiplying by 3. In this case, every point should be exactly 3 times as high. If I was multiplying by 2, it would be twice as high. If I multiply by 10, it's 10 times as high. But that's a good way to think of the stretch, is you're stretching the whole graph, but if you focus on one point, it gives you a good idea of that shape. All right. So, when you go to do a graph, the key to a graph is to know how to do these transformations separately, but also to be able to do more than one or even all of them at the same time. So when you're doing these graphs, step 1 is to identify and sketch the function from our library. The first thing we talked about today. You can't do a transformation if you don't have something to transform. So you get that starting graph down. You got to know those 5 graphs I showed you. Start with one of those. Now, in order, we reflect if we need to. Remember, you don't need to do every transformation in every problem. We stretch if you need to, and we shift, again, if you need to. You may have to do all 3 transformations. You may only have to do 1 or 2. It depends on the problem. What I will say, though, steps 2 and 3 can go in either order. You can reflect and then stretch, or you can stretch and then reflect, but I would definitely do the shifts last. And the reason is the reflecting and the stretching both stretch from the x-axis. You know, you're reflecting over the axis, or you're stretching away from the axis. If you shift it up or down first, you're not stretching from the axis anymore, and it makes those 2 transformations much harder to do. You still can do it, but it's harder that way. So I definitely suggest to you guys, you can do 2 and 3 in either order, but it's going to be much easier for you guys if you save the shifts until the last transformation. So let's finish up with a couple examples here. Let's say we want to graph this one right here. We have -2 times absolute value of x minus 1 plus 4. And what I'm going to do for the notes is I'm just going to make a list of my steps. So step 1, I identified my starting function from the library, and it's an absolute value. I can see that. You know, I see that absolute value of symbol around the x minus 1, and I say, before I think about the -1 in there or the -2 out front or anything like that, I recognize that this is an absolute value graph, and I'm going to start with that. Then I say, well, I have to reflect this thing vertically. And I see that because of this negative right here. If you have a negative out front, that's a vertical reflection. Now, I don't do a horizontal reflection. The way I would know that there's a horizontal reflection is if it was a -x instead of a regular x. Okay, this also has a stretch, and the stretch comes from the 2 right here. If you're multiplying the absolute, once you recognize the absolute value as your main function, if you're multiplying it, that's a stretch. And then this one actually has 2 shifts, and I put them together into one step, which is perfectly fine. I have an up 4 because of this plus 4 right here, and I have a right 1 because of this -1 right here. And I'll do those 2 last, and I'll do those 2 together in one step. All right, so I'm going to clear this out, give myself a blank graph to work with, and also clear out all those circles that I drew in there. And let's draw. Let's do our graph. So first of all, since I said I'm starting with absolute value, let's draw that first. No transformations at all. Absolute value is that V-shaped graph that cuts the first and second quadrants down the middle. Extend that one a little. Okay, it's a little bit hard for me to draw in this program, but I'll do the best I can. Okay, then I said step 2, and I'm going to do my transformations in the same color I circled them in. Step 2 is I'm going to do a reflection. I'm going to flip this thing from the top of the graph to the bottom. Well, then it's going to look like this. So I'm on the purple one now. And remember, you're always working from the most recent one. So I'm going to leave them there to show my work, but we're now working with the purple graph. Now, the third one, this is probably the hardest one, and that's going to be the stretch. So we said when you're doing a stretch, take any point on the axis. So I'm going to take that vertex of the V and imagine pinning it down. That one's going to stay right there. You're always stretching away from the axis. So I'm actually stretching this one down. So imagine grabbing the 2 points of the V and pulling them down and stretching them out. Now, if you want to see how far to stretch, what you can do is you can, like I said, pick 1 point on that original, like this one right here. That one is down 2 squares. If I want to double that, it would be down 4 squares. It would be right there. So what you want is the V going through that point like that, and then it's going to be symmetric. So I'll just draw another one. So when you stretch the V or a parabola, it works this way too, it actually ends up becoming skinnier. So black was absolute value, purple was with the negative, it was reflected, red is reflected and stretched. The last thing I want to do to finish this out is the two different shifts. I want to shift this thing up 4 and right 1. So what I'm going to do is I'm going to focus on that vertex again. I'm going to start with this point right here in the middle, and I'm going to take it and I'm going to move it up 4 and right 1. Now basically what I want to do is recopy the red graph exactly, but starting from that blue point. So it would be kind of like this. That sort of upside down, skinny, V-shaped graph. Now the light blue one, that's my final answer. And I know it looks very messy when I draw them all on top of each other. I did that just for the notes so you guys can really see each step. But basically what we've done is we've taken an absolute value graph, we reflected it, we stretched it, and we shifted it. And when we do all three of those things together, we end up with that light blue graph thing. All right, I want to do one more example with you guys. And we have 3 times the square root of negative x minus 4. And what I'm going to do, I'm not going to write out each step like I did in the first example. I'm going to go straight to the work. And because it's a square root, I identify that first. Before I do any transformations at all, I can recognize that this is a square root graph. And that's the one that looks like the top half of a sideways parabola, like that. So there's my original graph. Now for step 2, I'm going to focus on this negative here, and I'm going to say negative x is a reflection, but it's horizontal. So basically it's going to take that and it's going to flip it to the side here, like that. Okay, step 3. Let's do our stretch. So because I'm multiplying by 3, it's going to stretch the height by 3. And again, you can do kind of the same thing I did before with the stretch. We're going to pin this point down. That one's not moving. I'm going to pick a random point on the graph, maybe this one here, and I'm going to say that was up 2 squares. So if I want to triple the height, it would be up 6 squares. So it's going to be up here at 6. So basically what I want to do is draw kind of a square root graph, and I missed the point because it's a little bit hard for me to draw on my projector, but you get the idea. It's that stretched out square root graph. Now, final answer here, I'm going to take that red graph and I'm going to move it down 4. There is no horizontal shift this time. There was no extra number being added to the x. So all I have to do, let's start with this point in the middle again. Let's move it down 4, and what I want to do is recopy that red graph, but from starting from right here. So you'll get this graph kind of like that. Something like that for your final answer. And I use the same colors I did in the last example. The light blue one is your final answer. It is a square root graph that's been reflected horizontally. It's been stretched times 3, and it's been shifted down 4. All right, you guys, I hope this helped. As always, if you have any questions, email me. Otherwise, I will see you in class next time.